principles that allow us to prove that it's NP-hard. But really what I want to get to in this lecture is I want to get to some of the basic structural assumptions about A that allow you to say that some underlying sparse solution is itself the answer to star, that it's the unique answer, that it is the sparsest solution of some given linear system. And the things that will point us to cases where X is the uniquely sparsest solution will also be the types of properties that we'll be able to exploit to actually get algorithms for finding X too. So it's the same usual theme in this course that we look for when the problem is unique and robust, to look for where we can hope for algorithms, and that'll be exactly the case here. So let me start with some basic observations about this problem just to help you digest it. So the first simple claim so if A has full column rank, then star can be solved in polynomial. So any idea how to prove this? It's been a while, we've had a long break, so let's start off with an easy one. So I guess my hint is, oh sorry, is there an answer?
Is there only one solution?
Yes, so there's either 1 or 0 solutions in particular. I mean, it could be, even if A is full column rank, there could be no solution to this. If, for example, B is not in the column span of A, but that's a case where there'll be no solution for X. In general, when B is in the column span of A, then there'll be only one solution to this linear system. So you can just ignore this sparsity constraint in general. Whatever one solution you find is the only solution, and whatever sparsity that has is the best you can do for star. So that's at least one case where we know this problem is easy to solve, is the case of full column rank. So let me make this precise. So the point is that if B is not in the column span of A, then star has no solution. And if B is in the column span, A equals B has a unique solution. So all we have to do is solve this linear system, find any solution, any old solution, and it's the optimal solution to star. So that's the first simple claim, just to make sure we understand the facets of this problem. So are there any questions about this? Make sense? All right, second simple claim before we get to the interesting things. All right, in general, this optimization problem is hard. Is anyone surprised by this? Raise your hand if you're surprised. Good. All right, I would have been upset if someone was surprised. You shouldn't be surprised. These problems are always hard in general. But it still makes sense to understand what makes it hard, because then it'll give us a hint about how to avoid those gadgets and try and focus on where the problem might be easy. So in fact, we already talked about a general reduction. So does anyone remember the Kruskal rank? Anyone remind me what Kruskal rank is?
Maximum R for all subsets in a set of vectors that are independent?
Yes. So it's the largest R. So given a collection of vectors, it's the largest R so that every set of R of them are linearly independent. And we proved at some point we talked about Kruskal's uniqueness theorem was actually that the Kruskal rank is hard to compute. So just to remind you about this, so recall the Kruskal rank of A1 up to an in some m-dimensional space where you're thinking about m as being less than n in this case, is the largest R so that every set of R vectors is linearly independent. So for example, in the case where the Kruskal rank is m itself, it's saying every set of m vectors is linearly independent, and that's often called general position. If I chose, for example, n random points in m dimensions, almost surely the Kruskal rank would be m. But what we proved when we talked about Kruskal's uniqueness theorem is that computing the K rank is NP hard. Anyone remember this reduction?
Was it D sum?
Yes. And there was also, you remember there was this weird moment curve where we took determinants of this weird moment curve and they were related to the van der Waals. In any case, you can just assume this for now and remember that this proof is in the notes. You can look it up if you forgot it. But we proved that the Kruskal rank is indeed NP hard to compute. And from this, it'll actually be easy to prove that star is NP hard in general. So here's the idea. So what we're going to do is we're going to consider the following linear system. So what we're going to do is we're going to fix some special index I, and we're going to look at the AI column, and then we're going to create a matrix which has all but that column. So we're going to look for a linear system which has A minus I, so all the columns except for I, times X recovers this ith column, and we're going to try and find some solution that has the fewest non-zeros as possible. So we're going to do this optimization problem many times for each I. It'll be a many to one reduction. Let me call this particular optimization problem PI. So the key claim along the way to proving that star is NP hard in general is we want to show if we could solve all of these linear systems that we could indeed compute the Kruskal rank of a given collection of vectors. That's the idea. So now, the key claim in here is that PI has a solution whose number of non-zeros at most r minus 1, if and only if there is a set of R vectors including AI that's not linearly independent. So that's the key claim. So can anyone tell me why this is true? It should be immediate, actually.
We've just written the ith column as a linear combination of r minus 1.
Exactly. That's explicitly what this is trying to do. So the point is, when you're trying to use star as an optimization problem to solve an NP hard problem, you always have to worry about putting in a non-zero vector here. So all I'm doing is I'm guessing one of the columns that should participate in this R-wise linear dependence. And I'm looking for a sparse linear combination. So if we do have a solution, we've explicitly written AI as a linear combination of R minus 1 other ones. So it means that this particular optimization problem, PI, has a solution with sparsity at most R minus 1, if and only if there is a set of R vectors which AI participates in that violates this Kruskal rank condition. So now all we have to do is we can solve this optimization problem for each I, and then there is some solution with sparsity at most r minus 1 if and only if there is a set of r vectors, any set, which actually is linearly dependent. Does that make sense? That's the end of the NP hardness proof, right? So in general, we definitely can't solve star. So does this proof make sense? Any questions about it? All right, so now what we've established is one case where star is easy, one case where star is hard. But the more interesting part of the sparse recovery literature is in understanding what sorts of conditions on A, beyond things like just full column rank, allow you to actually solve this problem, star, in a meaningful way. So that's really going to be the focus. We're going to focus today on a condition which is the easiest to digest. It's called incoherence. You also might have heard of restricted isometry property. That's also in this literature. That's yet another type of condition on A, which will allow you to solve this optimization problem through a relaxation. So that's what we're really going to be interested in for this mini unit, is what sorts of conditions on A impose uniqueness and allow us to design algorithms. Okay? Who's seen compressed sensing before? All right. Okay, so now our new question, our main question really in this unit, is what sorts of structural assumptions on A allow us to solve star? All right, so let me introduce the notion of incoherence, which is one of the main things we're going to be working with. Now, the fun thing about incoherence is you can prove, what I'm really going to do is I'm going to introduce incoherence. Then I'm going to show you what are called uncertainty principles. These are things like, a signal and its Fourier transform can't both be sparse, so we're going to prove that via incoherence. And then we're going to show how that actually implies, first, that this type of optimization problem star has a unique solution under some nice conditions. And then in the next lecture, we're actually going to show algorithms for recovery. So that's the outline for today. But let me start off with this notion of incoherence, and let's talk about it. All right, so this is the key definition that we're going to be using. So we're going to work with some matrix A, which will always be m by n. And we're going to say that it's mu incoherent if for all pairs of columns, their inner product is small. So that's the idea, is that incoherence is a type of assumption that allows us to say that the columns of A, in general, we won't be able to assume that they're orthogonal to each other, that they actually have zero inner product. But even in the case where we have many more columns than dimensions, what we're going to impose as our structural assumption is that they be quite uncorrelated with each other. So how uncorrelated? Mu uncorrelated. So does this definition make sense? A lot of cases we'll focus on, the columns of A will always have unit norm. So you can really just ignore this part of the definition, and you're really just saying that for unit norm columns, that their inner product is at most mu over root m. The smaller mu is, the tighter and tighter this is as a constraint. So just to make sure that we're on the same page, so if A is orthogonal, mu is 0, that's great. But the other claim, which I'm going to leave as an exercise for you to prove, is that if n is larger than m, so it has more columns. So an orthogonal matrix can only have as many columns as it has rows. But once you start having strictly more columns, then what I claim is mu is at least 1. So this will always be the case we're interested in, is we'll always be interested in cases where there are many more columns than rows. Now the point is you can't get away with perfectly uncorrelated factors, but roughly the best you can hope for is mu some constant or polylogarithmic. One other way of thinking about this is if I were to generate A randomly by choosing its columns as random unit vectors, then even if I choose the number of columns to be some large polynomial in its dimension, you'll still have columns whose inner product has mu about root log n. So this is the type of condition which is satisfied, for example, by random dictionaries with some polylogarithmic mu. And actually, there'll be one example that we return to throughout as sort of guiding intuition. So let me give you that, and we'll see that it's incoherent. But I'll specialize a bit of our discussion just to this one example. So this one example, which is going to come up again and again, is what's called the Spikes and Signs dictionary. This is actually the example which motivated a lot of the work that I'm going to tell you about, so I'll tell you more about that in a second. But this is a very simple over-complete dictionary with more columns than rows. All we do is we create a m by 2m matrix just by concatenating two different bases together. One is the standard basis, so we put in the identity matrix in here. And the other one is the Fourier basis, so what we're going to put in is the DFT matrix. In particular, the ij entry is just omega to the I minus 1 times j minus 1 over root m, where omega is the mth root of unity, so it's just e to the I 2 pi over m. So it's a complex number, which is 1/nth of the angle, and you raise it to the nth power, you get back unity. And so all you're going to do is the entries of this DFT matrix are just powers of omega. So hopefully you guys have seen the DFT matrix before, but this is called the Spikes and Signs dictionary for obvious reasons. Spikes and signs. Those are basis elements. So in general, we'll be looking at what sorts of signals you get out from sparse combinations of spikes and signs. So the original motivation actually goes back to Bell Labs and really beautiful work of Logan. Sometimes what I'm about to tell you is called Logan's phenomenon. We're going to prove an uncertainty principle for this type of dictionary. And it's called Logan's phenomenon because what he was interested in were cases in Bell Labs where what you transmit on some noisy channel has a small sparse representation as signs. You're only using some frequency representatives, but then it's also corrupted by impulsive events, and these are the spikes. So his basic question was actually, if the signal you observe, for a priori reasons, is a sparse combination of spikes and signs, can you actually recover it uniquely? So that's one of the basis starting points for sparse recovery itself. So we'll keep coming back to this example because it'll be a tight example for a lot of the things I tell you. Are there any questions about this dictionary?
We want
Makes
to
sense?
live in complex space, I guess, or
Ah, good, yes. Thanks. Any other questions? Dictionary makes sense, right? All right. So the key lemma that we're going to prove, which we're going to use for a lot of things today, this is called an uncertainty principle. But maybe you won't see quite yet why you should interpret it as an uncertainty principle. But the basic idea, and this is a more general phenomenon, but I'm going to state it in one particular case. Well, we're going to suppose that some dictionary is the concatenation of two different bases where are orthogonal. And we're also going to assume that A is mu incoherent. So this is just a generalization of this type of example. We think about what if our dictionary is composed of two different bases, orthogonal bases. These are as nice bases as you can think, but they're somewhat uncorrelated with each other. Then what we're going to show is that if we represent some vector as its different representations in these bases, so we represent it as alpha times u or beta times v, and b is non-zero, then we can actually lower bound the number of non-zeros in this representation. So that's the key lemma, is that actually if you have two different bases and they're uncorrelated with each other in the sense that they're incoherent, so that's a constraint on if I take, for example, a column in U and a column in V and take their inner product, I'm constraining how large their inner product can be. That's really a statement about how redundant these two representations are. Then if you have this constraint that they're not redundant representations, that they're incoherent, then what you get is that you can't simultaneously make the number of non-zeros in both of these representations small. Yep?
What do you mean by U, V, or orthogonal? Just that they're two different orthogonal matrices, or is it?
Two different orthogonal matrices. So like in the case of spikes and sines. So there we explicitly have one orthogonal matrix and another one. And all I'm saying is that you have two different bases, which you could use to represent anything, or orthogonal matrices, but they're non-redundant and uncorrelated with each other in the sense that they're incoherent. So this is actually the key lemma, which is going to pave the way for uniqueness. Right? But before we actually prove this lemma is actually deceptively easy to prove. It looks deep the first time you see it. It's not. Let's actually interpret what it means for the case of the spikes and sines dictionary, because that's where we can see why it's viewed as an uncertainty principle. So in the case where we choose U equals I and V equals this DFT matrix, then what we're really saying is that B is itself, I times B in an obvious way, but it's also equal to B times some beta. So what we really have is we have a representation of some signal in the standard basis, and we have its Fourier representation. So we have some signal and its Fourier transform. And what we're really saying is that if B is non-zero, because obviously if it's zero, both it and its representations are zero, we can't say anything about the number of non-zeros. But if B is non-zero, then actually we have the constraint that just applying the lemma directly, we have a lower bound on how many non-zeros in sum total you must have between B and beta. So the other question is, what should mu be for the spikes and signs dictionary? So remember that this is the spikes and signs dictionary, and this notion of incoherence is a bound on the inner product. These are all unit vectors, so that's fine, because I've chosen this 1 over root m as the normalization. If I choose any pair of unit vectors entirely in one basis, I get 0 inner product. If I choose 2 from here, same thing. But if I choose things that cross, 1 from here and 1 from D, the inner product I get is 1 over root m. So it really is a case where mu is 1. So in that case, we can actually set this to be 1. And what we're really saying is that any signal and its Fourier transform, if it's non-zero, have to have at least 2 times root n non-zeros. So at least one of the two, either B or beta, has to have at least root n non-zeros. So a signal, non-zero, can't be simultaneously sparse in both its time and frequency domain. So that's why it's called an uncertainty principle. You can think about this as being similar in spirit to something like, a Heisenberg uncertainty principle. You can't be concentrated simultaneously in 2 different bases. But actually what's nice about this general lemma is that a lot of times you think about that uncertainty principle as being something which is very coupled to time and frequency, which granted are as uncorrelated as you could ever hope for 2 different bases, which are orthogonal, but it's really not a statement about time and frequency as much as it's a statement about incoherence. So even if you have other pairs of bases, you still have this property that you can't be sparse in both of them. So it's actually a much more general phenomenon. In fact, it's even not hard to prove an uncertainty principle, which doesn't have the structural assumption that these things be orthogonal. If you just have an incoherence assumption about these columns, you can also prove an uncertainty principle, albeit with worse constants. So that's the way to think about this. So we're going to prove this lemma, but are there any questions about this? All right. I claimed that this lemma is easy. It is easy, actually. I think it's surprising the first time you see it. It's very easy. So the game plan is, let's prove the lemma, and then what we're going to do is we're going to apply it to show uniqueness conditions, which we're going to build on next time by actually showing algorithms that achieve those. But for the meantime, let's prove this lemma. So let me write the actual subscripts of the norms just to, we're going to be working with a few different norms here. So let me write out the subscripts to be explicit. So, the first part is that since U and V are orthonormal, well, we're really thinking about this vector B's representation in 2 different bases. That's the way we've set up this lemma right now. So we know for sure that the 2 norm of these representations are all equal. The 2 norm in the standard basis, the 2 norm in U, and the 2 norm of the representation in V. So that's easy. But now what we're going to do is we're going to use this to express the inner product between B and B two different ways. So now, if we think about it, if we take the 2 norm of B squared, then we can write this out just as BB transpose, which itself we can write out 2 different ways using our 2 different representations. I guess really if I'm working over complex matrices, I should be using the Hermitian, but let me just use the transpose to keep things simple. It doesn't really change anything. So this is just writing out what B is, 2 different ways in my 2 different representations. But now the key point is, what is this matrix? So it's an M by M matrix. And who can tell me interesting things about this matrix? Sorry, what?
Besides the diagonal, that looks new everywhere.
Yeah, actually, because, in fact, you're right. One should in general ignore the diagonals. But that would be the case where I look at A transpose A, and I actually have to worry about a column's inner product with itself. But here I'm explicitly, because I have this partition into 2 orthonormal bases, it's actually even simpler. That each of these entries, I claim, has absolute value bounded by mu divided by root m, just by our definition of incoherence. Actually, lots of these points is when you talk about more general definitions of uncertainty principles, where you don't have this partition into 2 orthonormal bases, you instead end up looking at A transpose A, and then you really have to look at the diagonals and the off diagonals differently. But that's actually the same way that you can prove these uncertainty principles in general. So maybe we'll have a homework problem on that. It's not too hard using Hirsch-Torrens theorem. But in any case, we have this matrix V transpose U, whose entries are not too large. And now what we can do is this gives us a nice way to think about what this inner product is. Well, we can pull out whatever the largest entry is here. They're all absolute value at most mu over root m. But now if you look at this quadratic form, each thing picks up a beta I and an alpha j term. So in general, what I'm going to get is sum over I and j of absolute value of beta I times absolute value of alpha j, right? So that's explicitly just applying the triangle inequality on this quadratic form because of the properties of this matrix. I'm just parenthesizing it so that I look at this quadratic form, and I know that all of the entries here don't have very large absolute value. So this is what I get out. But now we can think about this more simply as all this is it's mu over root m times the L1 norm of beta times the L1 norm of the alpha vector. Now we're in good shape because what I claim, it just follows from Cauchy-Schwarz, is that the 1 norm of alpha is at most root times the number of non-zeros times its 2 norm. So in general, the 2 norm for a vector can be much smaller than its 1 norm. If you think about a vector which is length n, which has 1 over root m everywhere, then in fact its 2 norm is going to be 1, but its 1 norm is actually going to be root n. But you can always up or down the other direction. So just like in that case, they're root n off. In general, you can relate the 1 norm and the 2 norm based on how many non-zeros. So I just take square root of the number of non-zeros, and that'll allow me to upper bound the 1 norm by the 2 norm. So this is just Cauchy-Schwarz. But what this now immediately implies is that we have mu over root m times square root of the number of non-zeros times the corresponding two norms. So remember that now what we had was we had this chain of first equalities and then inequalities. So right here we've got the 2 norm of b squared, and lo and behold, what we pulled out was the 2 norm of alpha and the 2 norm of beta. So we know from this equality that this is just the 2 norm of b squared. So we can just cancel this on both sides. And now we're in business because we have something that looks like an uncertainty principal. We're almost done. Let me just finish up on this board. And now what we can do is we can apply the AM-GM inequality. And we know that this geometric mean between the sparsity of alpha and the sparsity of beta is in fact upper bounded by its arithmetic mean. So at the end of the day, what this gives us is exactly our bound we pull out to the other side. We end up getting 2 root m over mu is a lower bound for the sum of the sparsities. And that finishes our proof. Okay? So are there any questions about this? Yep.
So we only use that the columns of U are sort of separated with each column of V, right? But not the column.
Incoherent, right?
Yeah, there's distance between each column of U and the ones of V, but not within U and within.
So we sort of did, because U and V, in this simplified lemma of the uncertainty principle, we proved it in the case where U and V are orthonormal. So we're explicitly saying that their inner product should be 0. But another way of saying this is that in general, when you don't have this partition into 2 different bases, like you have for the spikes and signs dictionary, well, in general, you look at A transpose A, and then what you're going to have is you're going to have 1s along the diagonal, because you're just taking a vector and taking its inner product with itself. But off the diagonal, you have an incoherent matrix, which has small absolute value entries. So the way to think about it is, I've explicitly said that A is U, V, and when I take A transpose A, what I end up getting now, in the case where U and V are orthonormal, is I end up getting the identity along the diagonal because these entries correspond to taking columns of U and taking their inner product with other columns of U. So I get 1s along the diagonal and 0s everywhere else because of the orthogonality. But what I'm really saying is that this in here is, this up here is my V transpose U. And I'm really just saying that all of the entries are small. So in general, when you talk about dictionaries which are not the unions of 2 orthogonal bases, you won't be able to have that there are many 0s here. Instead, you'll just have that they have 1s along the diagonal and have small off-diagonal entries. But that's actually enough. You just end up losing extra constants. And you can still prove the types of uniqueness bounds that we're going to prove. So I'll leave that as an exercise. Yep.
Is there a reason we're stating it for their sum when we get it for the product? Like, in most applications, do you just use it?
Actually, the way we're going to use it when we prove uniqueness will be for the sum. Now, it's true that this thing is stronger, right? So, you could state it this way, but I think the intuitive corollary that a signal has at least root m non-zeros, or its Fourier transform does, is the main reason we're going to this sum, and because of the uniqueness applications we're going to use downstream. So we'll see that in a second. Are there other questions about this? This is an important dilemma, so don't be afraid to ask me all sorts of questions about it. Make sense?
I'm going to have a quick
Yep.
question. The Cauchy-Schwarz part
Yep.
seems kind of, I'm not quite sure why that's true.
Okay. So here, for example, this one norm between this vector is what you're actually doing is, let's say in the case where alpha has only non-negative entries, then what this is it would be the inner product between two vectors. The alpha vector and a vector which picks out ones for where the entries are, which by assumption are all non-negative. Now, in general, if they're not non-negative, you would have to put their signs in here instead, but you would still get that this one norm is the inner product between a vector and a sparse vector. So now when you apply Cauchy-Schwarz, what you end up getting is that this inner product is the product of the two, is at most the product of the two norms of the vectors. Well, lo and behold, we have the two norm of alpha, and this is the two norm of this vector, because, just by calculation. And in general, I just stated it this way when alpha is non-negative, but it's obvious you can do it even if it has positives and negatives, because you would just have something which has plus ones and minus ones, corresponding only to the non-zeros and equal to the sign. So that's how you prove that. Any other questions about this?
That's cool.
I think so. Yeah, these uncertainty principles are shockingly easy and more general than you would think, actually. I don't know, maybe we'll talk about weirder uncertainty principles later, but I'm not sure I can do it without a lot of background, so we'll see. Okay, let's use it. So the first thing we're going to use it for is we're going to use it for establishing uniqueness. So let's do that now. Well, actually, wait, let's do something fun first before we do that. So we have the spikes and signs matrix, and we have this key lemma. Anyone think it's tight? Let's have a vote. Who thinks it's tight? Yeah, why would I show you something that's not tight? It's tight. But actually, it's tight for the spikes and signs matrix, which is kind of cool. So there are ways that you can derive stronger uncertainty principles with more assumptions, but at least with this minimal number of assumptions, it really is tight. So the idea is that any guesses what B we're going to use? So really what I want to do is I want to give you an example of a signal that has root m non-zeros, and its Fourier transform has root m non-zeros. Exactly root m. So any ideas? Yeah.
You can take a Dirac comb.
Yes. The answer I was looking for was Dirac comb. So what you do is you create a length m signal in which all you do is you have ones at evenly spaced locations, and everything else is a zero. So the way to think about this is that in general, this is called a Dirac comb. But the important property is that the Fourier transform of a Dirac comb is a Dirac comb, which is good. But actually, if you think about a Dirac comb, you can define with any sort of spacing you want. So actually what happens is that the tighter that you space this, the further out the spacings of the Dirac comb. Another way of thinking about this is that's exactly what the uncertainty principle is telling us has to happen, because we're really saying something about the product of the number of non-zeros, at least being something. So the tighter you make this, if they were all just unit 1 apart, then all you have is a single spike on the other side because it's a constant term. But in general, you spread out the spikes by root m, so that there's root m of them. And then you get a Dirac cone in which there's root m of them, and they have this root m spacing as well. So this is a tight example of a signal which really does have root m non-zeros in it and its Fourier transform. Now, there are situations where you can prove better uncertainty principles if you exclude this type of periodic behavior. But that's a whole other can of worms, and those are very technical to state. Does this make sense? All right. So now let's use this lemma for proving uniqueness. So we're going to prove uniqueness just in the case where we've proven the uncertainty principles. So let me focus on the case, even though these things will hold more generally for arbitrary incoherent dictionaries. Let's say that we're, again, working with these nice types of dictionaries where U and V are orthogonal. And we're thinking about this as a, m by 2m matrix. So it's over-complete in that it has more columns than rows. So it for sure cannot be in this case where we have full column rank, where things are easy and we can ignore sparsity and just solve a linear system. These are cases where we really do need to assume sparsity to be able to solve the types of inverse problems we're interested in, that, for example, Logan was interested in. And what we're going to show, and we also assume that A is mu incoherent, because if you have two really redundant bases, then there's not much you can say. Now, the way that we're going to look at this is we're going to plant some sparse solution. And we're actually going to have conditions on how sparse that solution is compared to this incoherence property to say that that planted sparse solution is itself the answer to star, that it is the sparsest linear combination of columns in A that recovers what we observe. So we're thinking about this solution, x hat, as being planted, and we're going to assume that its number of non-zeros is strictly less than root m over mu. So we're just taking our incoherence principle, dividing it by 2, and making it a strict inequality. Then what we're going to show is that at least in principle, if we could solve this computationally hard optimization problem, we'll talk about algorithms to do it in this setting next time. But if we could solve this computationally hard problem star, find the sparsest solution to a given linear system, then actually x hat is its own answer. And I should add a caveat that here what I'm saying is we're setting this B to be what you would get if you multiply the sparse planted solution times A. So you've set up this linear system where you have this B, which has x hat as a valid solution. But you look, is there possibly a sparser x that also solves the linear system? And the claim for this corollary is that there isn't any, if x hat is itself sparse enough based on how incoherent the dictionary is. So does that corollary make sense as a statement? And now we're going to prove it. So are there any questions about this? Okay, so this isn't too hard to prove. So what we're going to do, and this will actually be the standard way that you prove uniqueness for sparse recovery. we just suppose that, that there is some sparser solution, and we're going to use it to violate our incoherence and our uncertainty principle. This is actually the same pattern which you use to reason about things like RIP, is you just assume that there's some other solution, and then figure out a way to derive a contradiction with your RIP property itself. And we'll get to that later. So suppose that there's a solution which has at least the same sparsity. Now this will be short but subtle. So we just look at their difference. And what I claim, so we know that a times y is itself 0, it's in the kernel, because multiplying by x, a times x, we get b, a times x hat, we also get b, so when we subtract the 2, we get 0. But the important point is that now we can actually think about this itself. What we can do is we can take this y vector, which resides in 2m dimensional space, and we can partition it into alpha y and beta y. So just taking the first m coordinates and the second m coordinates. And now what I claim is that this guy is non-zero. So can anyone tell me why? This is the only subtlety in this. After all, in order to apply the uncertainty principles, we need to assume that the vector itself is non-zero.
If it were 0, then so would the
Yes,
and alpha
that's
y.
it. Exactly. If this were 0, well, then this has to be 0 too, right? And then because these are orthogonal representations, we would know that actually the representations themselves are both 0 too. So that's the claim, is that this vector itself is non-zero. And what this allows us to do is we can just take u alpha y equals minus this guy. And we can think about this as some, some vector c, which now we know is non-zero, and we have c on both sides. Actually, let me just write it up there for simplicity. So now we're in good shape because we can, it looks like we can apply our uncertainty principle, right? We have some non-zero vector which has two different representations in u and v. One of the representations is alpha y. The other one is minus beta y. And we know now through our uncertainty principle, oops, gives us that alpha y plus the number of non-zeros in alpha y plus the number of non-zeros in beta y is itself at least 2 root m over mu. And I claim that this has a nicer expression that we can use instead. So can anyone tell me what this left-hand side is in terms of y? Easy questions, yeah, exactly. So this entire thing is itself equal to the number of non-zeros in y. Y is just this disjoint set of these two vectors, so we get some lower bound on the number of non-zeros in y. And now we're actually done, so there's one last trick. Unfortunately, I keep just barely running out of space, but let's do it over here. So who can finish the proof for me and get a contradiction? So now we have a lower bound of the number of non-zeros in y, and y is itself x minus x hat.
Even though the zero norm is not a norm, it still satisfies the triangle inequality.
Yes.
So just
Yes. So let me state it this way, which is that, y, recall that y is x minus x hat, which then it's easy to see that the number of non-zeros in y is at most the number of non-zeros in the two vectors. Every non-zero y has to come from at least one of x or x hat. We have to be able to blame one of its non-zeros. So now all this is going to give us is that, by assumption, we had that x hat 0 is strictly less than root m over mu. And we're also assuming, for the purpose of contradiction, that there is a solution which is at least as sparse. So all of this, at the end of the day, tells us that we have an upper bound, that it's strictly less than 2 root m mu, but we also have this lower bound of y0 via the uncertainty principle. And that gives us our contradiction. Okay? Any questions about this? Okay, really no questions. All right. Let's do something else fun to sort of tie these things together. So who can remind me Grishkorin's theorem? Do you guys remember the circle theorem?
The eigenvalues are contained in a disk centered on the diagonal, and the rest of it is the radius?
Yes. So let's do an application just to tie all these things together, because there's actually a really tight link between all these things. So, recall Grishkorin's theorem, which we proved, was what we do is we take a matrix M, and what we said was that the eigenvalues of M are themselves contained in the union of some disks. So each of these disks is centered at a diagonal entry, and the radius of this disk is Ri, where Ri is the sum of the off diagonals. So you remember what this allowed us to say were things like, if we have a small perturbation of the identity. So the identity would be a matrix where this would be a 1 in here, and the radius would be 0, because you look at the sum of the absolute values of the off diagonals and you get 0, right? And we know that the identity has all of its eigenvalues equal to 1. So Grishkorin's theorem was the simple theorem that we proved. We proved it in the context of trying to understand how robust our methods for tensor decomposition are to noise. But it allows us to say things like, if you have the identity matrix, and then you add very small perturbations in the off diagonal, then you can't actually make it be degenerate and have rank less than n, because these radii will be small enough that none of these diffs actually contains the origin. So that was one of the things we proved. But now actually a question I got after class, I think from you, was, can you improve this? This sounds like a really weak bound, right? Because maybe you can do something like you can look at the 2 norm of the off-diagonal entries. which would be much better if you can do it, but that's actually all these things, the spikes and signs dictionary is actually going to give us that Grishkorin's theorem is tight. That'll be another consequence of it. Because the fact that it was tight for this uncertainty principle gave us two different representations of the same vector, but it'll actually show us a sparse vector in the kernel of that matrix. So what I claim that this implies. So if you think about taking, well, actually, let's first back up a second. Let's think about applying Grishkorin's theorem here. So when we take A, which is the spike and signs dictionary, and then we take A transpose times A, what we end up getting is exactly this diagram with an identity along the diagonal. And the entries here have absolute value at most 1/√n. So one of the things Grishkorin's theorem can tell us, so if you think about creating a k by k submatrix of this. So you take k different columns and you look at those columns and the corresponding rows, and you create some k by k submatrix. Then what you're still going to have are you're going to have ones along the diagonal, and your off diagonals are still going to be at most 1/√n. So if you think about what Grishkorin's theorem is saying, is if I just look at this k by k submatrix, then as long as k is smaller than about √m, then what you're going to have is that those radii are themselves not going to contain the origin. So we would have that any less than √m by √m matrix here has is invertible, has no kernel, right? Would be an immediate consequence of Grishkorin's theorem. But I claim that if you thought that there was going to be a 2-norm version of Grishkorin's theorem, then actually the fact that spikes and signs is tight for this uncertainty principle tells you that it isn't. So one way of thinking about this is we take this A transpose by A matrix, and we look at this Dirac comb, which is really what we're saying is that A times X is 0 for some signal X, which has exactly 2√m non-zeros. Because all we would do is that A times X is just some sparse linear combination of spikes and signs. And what I just said is that there is a signal which it and its Fourier transform are both sparse. So in fact, what that gives us a way of doing is we can take this signal, this Dirac comb, and we can represent it one way with some sparse combination of these spikes. But we can also represent it another way with some sparse combination of signs. So subtracting those two different representations, we get exactly 2√m non-zeros. And yet, because we're representing the same signal twice, it and minus it, we end up getting 0. So what that means is that there actually is an X, which when we multiply by A transpose times A, we get the all 0. So there really is a 2√m by 2√m submatrix of this A transpose A matrix, which really doesn't have full rank. So it tells us a statement in which Grishkorin's theorem really is tight. That usually you use it to say that large submatrices still have full rank or are still close to orthogonal, but there are limits to it, which again come from the spikes and signs. So are there any questions about that? All right, so next time what we're going to do is we have this corollary that when we plant a sparse enough solution, that if we could solve star, at least this original solution would be the unique minimizer to star. But what we're going to do is we're actually going to show that under these types of incoherence conditions, you really can solve star. And the way that we're going to do that, there are a ton of ways to solve star under these conditions. You might have heard of like L1 minimization, that's one way. What we're going to do is we're going to give a simple greedy algorithm, which all it does is it picks out the columns in A that have the largest inner product with the current residual. You start off with B, and then you keep adding non-zeros to your support in that way by picking out some column with the largest inner product, subtracting off as much of it as you can, and continuing on the remainder. So we're going to see that those simple algorithms do work. And just to give you a roadmap, that's all we'll really talk about for sparse recovery. We're going to move on to, after that, is sparse coding. Those are settings where, all of this is in a setup where we have AX equals B, and we don't have X. We have some really underdetermined linear system where we know A and we know B, and we want to solve this inverse problem by virtue of the sparsity of X. Sparse coding is a setting where maybe the right basis that makes all of your signals sparse is actually not known to you. So what if A is unknown, but you have many examples of A times X equals B, and you know those right-hand sides? Can you find one common basis that allows all of your signals to admit a sparse representation? So that's the version of the problem that I think has a lot more applications to learning. It was proposed actually originally by neuroscientists as a way to understand how the visual cortex got the types of receptive field properties it does have, that maybe it was trying to learn a basis that enables sparse representations. So we're going to give provable algorithms for sparse coding, and that'll be sort of the roadmap for this unit. All right, thanks. I guess we'll end a little bit early today, but let me know if you have any questions.
Anchor, quick question. Could you explain again why it's non-zero?
Yes. What if this were 0?
Okay.
If this were 0, then the entire thing is equal to 0 too. So that would mean this is equal to 0. Now, if this and this were both equal to 0, then you think about representing this vector. Its representation would have to be 0 too, because it's an orthonormal basis.
Oh, okay. Yeah. Okay,
It
that makes
just comes
sense.
from this is 0.
Mm.
If this were 0, this would be 0 too, and both of their representations would be. And then
Because of orthogonality.
exactly,
I see,
and
I
then
see.
x would equal x hat, which is not a contradiction.
Okay. Makes sense.
Would you have a big time later today or tomorrow? Or?
I've got a deadline on Thursday,
Oh,
but
yeah.
I have a few minutes now, and I also have plenty of time on Friday.
Then Friday.
Let's do Friday then.
Yeah. Could you also answer my questions on Friday?
Yes.
Don't worry, I need to go to today, so.
Okay.
Yeah.
So
those, I saw that you responded, but I haven't read it in detail.
Okay, so the first claim is yes, it's just the dimensions of the so there's transition matrices, and there's also observation matrices. So transition matrices just go down the hidden states, and observation matrices go from the hidden state to the observed state. Now the issue is that that's actually just so first there are a bunch of problems. So one of the problems is that the matrix which goes from the hidden state to the observed state has, the hidden state has 4 degrees of freedom. There are 4 states for it. The observed state is only 2. You either observe a 0 or 1. There's no way that that transition matrix can be full rank just by virtue of its dimensions. But even more seriously is that when you actually look at the transition matrices, even the transition matrices, even though they're 4 by 4, there will be 2 repeated rows.
Oh, okay.
Because what the current state has, it has the running parity, and it has the thing it's about to output, that it's already taken into account in the parity. So it doesn't actually matter what the thing you're about to output is in terms of the transitions. Your transitions only depend on what your current running parity is, because you then generate what your next bit is and update your parity. But it has nothing to do with the thing you've already committed to outputting. So that's the issue. So there are a bunch of issues there. I think you're right that the indices are out of order for that.
Yeah,
so I should fix that. But
it shouldn't be important.
Yeah. But the other thing to think about is when I described phylogenetic reconstruction, you should think about why it doesn't really matter that the nodes have different alphabets. So I claim that there's no extra generality, that all of the algorithms I gave you still do work, you know, essentially the way I described them in that setting.
Okay. I'll think about that.
Yeah. So think about it in the special case where for the hidden Markov model, let's say you know the state space of the hidden nodes, and you know the alphabet for the observed things. Then if all of those transition and observation matrices were full rank, I claim that you could still do everything that you know, we talked about for doing phylogenetic reconstruction, that you could still learn what those transition matrices are. But HMMs are a bit simpler because there's no unknown topology.
So you don't have to learn it.
You don't have to learn the topology, right? The same way that we use like Steele's metric to learn with these quartet tests. You don't need to do that, it's known. All you want to do is learn the transition and observation matrices. But the approach that I gave you based on, you know, creating a tensor decomposition doesn't really matter that alphabets are different for different nodes.
But the main point is basically that if it weren't full rank, then we could solve noisy parity.
Yeah,
that's a big issue.
Yeah, exactly. I mean, you know, you should also think about why that particular example doesn't work. But even at a broader level, we probably can't solve noisy parity. So, you know, the things which are barriers in that instance to, you know, solving HMMs really should be a barrier in general. There are things about that example that are important to know that, you know, some of these problems you really can't get around.
Okay, why is it the two rows are the same again? Could you explain that again?
So you have a hidden state, which what it has is it has 2 bits. One bit is the running parity total, and one is the next bit you're about to send out on the observed state. Right?
That's true.
But when you generate the next guy, you think about how you're generating the next hidden node.
Okay.
You want to generate a new bit, and you want to update the parity.
Yes.
How you choose the, you know, that end state doesn't actually depend on which bit you're about to output. Because you've already incorporated that bit into the running parity.
I got lost on who you did. Could you repeat that? Sorry. Maybe you should write it down. Sorry, Anchor.
You're at some hidden node.
Yeah.
You're trying to go to some hidden node. The state that you have here is just a pair of bits. This bit represents the running parity.
Yep.
And this says, you know, up to state I.
Yep.
So this is the parity on the I of things, but you haven't even outputted the I of bit yet. This is the I of bit.
Okay.
So this bit just goes straight down here and you output it. But when you think about what the next thing is, you have to generate the I plus first bit, and then you have to update the parity. But none of that depends on xi, because xi has already been accounted for.
Okay, I see.
So that means that there are, you know, it's a 4x4 matrix, but there are explicitly 2 different rows that have the same transition probabilities, because these are ones where they have the same running parity, but they have different output bits. That doesn't change what your transition probability is to the next hidden state. It only affects what you output down here.
Okay. Okay.
So the transition matrices really are not full rank. Even, I mean, they're 4x4, so you could hope they are, but they're not.
Okay. Cool. I think, was that everything? I'll take a look at the email and think about my questions again before I ask you again.
Okay, sounds good.
Cool.